It's common notation in math to have this d squared over dx squared to be the second derivative. But that is wrong. First of all, what does it mean to take d over dx squared? That means applying the function twice. And, well, what is the d over dx function? Well, this is the d over dx function. Takes in y, you take the derivative of y over dx. Now, some of you guys may come here and say, this d is not really a function. And I have a completely legitimate theory for why d can actually be a real function. But for right now, just stick with it. And for the sake of simplicity, you don't need the parentheses. So, yeah. So dx is actually d of x, and dy is actually d of y. So just remember that juxtaposition means function evaluation or composition. So with this new second derivative formula, well, what is the derivative of the derivative? What is d over dx squared? Now, plug that in using our previous one, use the quotient rule, and you get this. Now, this is a little bit ambiguous because we're using squared here, what means applying a function d twice, but here this means squaring a quantity, as in multiplying dx by itself. So I'm going to introduce some new notation. So if it has 2 in the superscript on its own, that means that it's applying a function twice, and then I have this tick mark here to show that it's multiplying. So divide this by dx, and you have your function for the second derivative. Yay, this is it. This is so wonky. First you see the familiar d squared over dx squared, but then you're subtracting this weird term. What's that for? Well, I hope I can motivate this by looking at a pressurized equation. So let's look at this. Y equals t squared plus t, and x equals t squared plus 1. So, take the derivative, get dy is 2t plus 1 dt, dx is 2t dt, do that to find dy over dx. That is just 1 plus 1 over 2t. So, you could take the derivative of that. Remember the chain rule, so you take it with respect to d and then do dt over dx. Then do some math, and you get the second derivative is negative 1 over 4t cubed. You can double check this yourself. It's correct. So now that we have that down, let's look at another thing we could do. So let's say I want to be naive. Let's say I believe that d over dx squared is d squared over dx squared. Like the common notation says. Well, could find d squared of y, just taking the derivative of this. Just use the product rule for 2t plus 1 and dt, expand it, and then you just square dx, simplify, and you get d squared y over dx squared. So this is nonsense. Like, this is obviously not the second derivative that we were looking for. So what's going on? Well, let's go back to this. We have d squared y over dx squared, and let's recall that our original formula. The second derivative is this same d squared over dx squared, but you're subtracting this extra term, d over dx times d squared x over dx squared. So why don't we plug that in for y? So go back to the equations we derived earlier, and take the double derivative of x, remember the product rule, and then just divide it by dx squared. So you get this, and plug that into your function. We have this behemoth as the second derivative of y. And you may be saying, hey, this looks even more crazier than what we got earlier. How is this the second derivative of y? Well, all it takes is some algebraic manipulation. You could pause the video to see all the steps. You could double check to verify it yourself. But in the end, you get the second derivative of y is dt squared, or negative dt squared, over 4t cubed dt squared, which, cancel out the dt's, is negative 1 over 4t cubed. So, I just demonstrated that this is an actually valid form of the second derivative through an example. And this is obviously not the second derivative. This is wrong, okay? The notation we use today is wrong. Stop using this as the second derivative, use this notation. Yeah, and you could actually extend this idea, well, taking the derivative, is just d over that function over dx, and then using the quotient rule, you could get, the third derivative, fourth derivative. I stopped at 3 because after that it just gets super complicated. But it shows that this is a completely valid formulation for the third derivative of dx. And so you guys might be saying, well, what does d mean? Like, you just, like, dx, in calculus you're taught dx is a very small infinitesimal. It's the limit. Like, the derivative is a limit of a function. How are you now taking d squared and d squared of x, like, on its own instead of, d over dx, which I'm used to? Well, stay tuned for a future video in which I actually define what d can be. And hopefully it's going to make the derivative, I guess, a lot more cleaner, Yeah, well, thanks for watching. Stay tuned for the next video. I'm out.